Okay, thank you so much for coming to this talk. This is joint work with Jay Liu and Xiaosheng Mu. All right, so algorithms are increasingly being used to make important predictions about people, including whether you need, say, a risky medical treatment, whether you're creditworthy and should receive a loan. Okay, recent empirical evidence demonstrates that many of these algorithms have error rates that vary systematically across different subgroups of the population. Okay, so for example, this recent science paper demonstrated that patients assigned to the same risk score, in fact, had different actual health risks depending on their race. Many of you probably know about this ProPublica article that came out in 2016, which was examining an algorithm used to help decide who should receive bail. And they discovered that this algorithm had a false positive rate that was twice as high for black defendants compared to white defendants. Okay, so these findings have increasingly encouraged algorithm designers to optimize their algorithms not only for the traditional criterion of accuracy, but also for some notion of fairness, usually modeled as some measure of how much the error rates vary across different groups. Okay, and what we wanted to understand in this paper was what the nature of that trade-off between fairness and accuracy actually looked like. Okay, so to formalize the trade-off, we introduced a fairness-accuracy frontier, which is going to range over the optimal points across a broad class of different preferences or optimization criteria. So this is going to range from everything from the designer who only cares about accuracy to the designer who only wants to make sure that error rates are equal across groups. Okay, now our results are going to characterize how this frontier depends on the inputs to the algorithm, with a special case being whether or not group identity is in fact given to the algorithm. Okay. And what I see as the main takeaway of this paper is that there's actually some things that we can conclude for policy which are going to hold in general across this broad class of very different views of how to trade off fairness and accuracy. All right, so let's jump straight into the framework. There's going to be a single designer and a population of non-strategic subjects. By non-strategic, I mean they're not going to actually do anything in the model. They're just there because we care about what we do to them. Okay, each subject is described by 3 variables. So first, there's a type Y. You should think about this as what the algorithm is trying to predict. For example, in the medical case, we might think about that as the true need for the medical procedure. Okay, there's also a group identity, for example, a race. And finally, a covariate factor, and here I'm using the econ term. This is also, you can think about it as a feature vector. So it's a covariate vector describing all the information that's on file about the subject. Okay, now the covariate vector is going to be observed by the designer and hence usable as an input into the algorithm. Y and G are not going to be directly observed, but we're placing no restrictions on the joint distribution of these variables. So for example, it could be that the covariate vector actually directly reveals group identity or even Y. Okay, now each subject is going to receive a decision, which is either 0 or 1. You can think about that as whether the procedure is in fact recommended. And that decision is determined by an algorithm that the designer chooses. Okay, so an algorithm formally is going to be any map from the set of possible values of the covariate vector into a distribution over the set 0, 1. Okay, so think about this as the algorithm gets as input this covariate vector. Okay, so your entire medical profile. It outputs a probability with which you are in fact recommended the procedure. All right, now to evaluate the algorithm and its errors, we're going to fix a primitive loss function. So a loss function is going to be any map from the decision taken for the individual and their true type, Y, into a number. So you can think about that either as the inaccuracy of that decision or as the disutility experienced by that subject. And then we're going to aggregate these losses within the different predefined groups. So fixing a group G and fixing an algorithm A, you guys can't see my mouse, right? Okay, good. We're defining the group G error for that algorithm as the average or the expected loss for individuals in that group when we use algorithm A for making the decisions. Okay, so here, just to walk through this expression more slowly, right, we're conditioning on the value of G. Okay, conditional on G, there's still heterogeneity naturally in X and Y because there's heterogeneity within groups. Whatever the realization of the covariate vector is, we're going to use the algorithm A to determine the decision that's taken for that individual. Then finally, we're going to use this loss function that we chose to evaluate the consequences of taking that decision given the true realized type of that individual, and then we're aggregating across subjects. Okay, so by appropriately choosing the loss function, we can nest many of the fairness metrics that are discussed in this literature. So for a simple example, if you're interested in false positive rates, we can very simply take the loss function to take value 1. If the decision is 1, the true type is 0, and value 0 otherwise. So in that case, the group G error is simply going to be the false positive rate within group G. Okay, so now, as we range over different algorithms, we're going to get different group errors. And fixing any primitive covariate vector x, we're going to define the feasible set to be all possible group error pairs that are implemented by some algorithm which takes that covariate vector as an input. Right, so here, all of the analysis is going to be about these pairs. So remember, this is the group R error using that algorithm. This is the group B error. And the designer is going to have preferences that help determine which of these error pairs is actually implemented. And here, so really the crux of the paper is we're not imposing a single preference over these error pairs. Right? Instead, we're going to consider a broad class of preferences that are consistent with a rather weak partial order. So we're going to say that a pair of group errors E, fairness accuracy dominates, another pair E prime. If E involves lower errors for both groups, we're thinking about that as higher accuracy. And moreover, the gap between the two groups' errors is lower under E compared to E prime. We're thinking about that as higher fairness. Right? So if E improves on both accuracy and fairness relative to E prime, the designer must prefer E. Right. So now this is the key object. We're going to define the fairness accuracy frontier given X to be the set of all pairs of group errors which are feasible, and moreover, fairness accuracy undominated within the feasible set. So there must not exist another feasible pair E prime which is better than E both in terms of fairness and also in terms of accuracy. Right. So we think about this fairness accuracy frontier as describing really the set of all possible optimal points across the sort of relevant designer preferences or optimization criteria. So just to give you a couple of interesting cases, right? So one interesting case is that of a utilitarian designer. So if all you want to do is minimize the aggregate error in the population, fine, you're included in our class. Right? At the other extreme, if you're a pure egalitarian, all you care about is trying to reduce the gap between the group errors. Okay, also fine, you're also included. And then there's all sorts of interesting intermediate cases. So for example, you might be a Rawlsian. You might say, what I care about is the larger of the two group errors, and I want that larger error to be as small as possible. Right, that also coincides with what's called group distributionally robust optimization in machine learning. Okay, so that's included. And then there's a whole class of constrained optimization problems, right? So you might try to maximize accuracy subject to the group errors not being too different from one another. Right, so all of these optimal points are going to be included in our frontier. All right, so now let's actually characterize it. So first, a quick lemma. For any covariate vector x, the feasible set is going to be compact and convex. If the set of possible realizations of this covariate vector is finite, it's a convex polygon like the one depicted here. And there's a couple of important points here that I want to point out. So also, by the way, so we have group R on the x-axis and group B's error on the y-axis. I'm going to show you many pictures that look like this. OK, so a couple of important points. First, for each group, let's identify the point that minimizes that group's error. Right, so Rx is going to be the feasible point that minimizes ER. Likewise for Bx. And third, we're going to define the fairness maximizing point, Fx, to be the feasible point that minimizes the gap between the two groups' errors. In all cases, if there's ties, we're going to break them in favor of aggregate accuracy. All right, now these points are easy to locate geometrically. So remembering again that group R's error is on the x-axis. Rx is simply going to be the feasible point that's most to the left. Okay, Bx is going to be the feasible point that's furthest down. And Fx is going to be the point in the set that's closest to the 45-degree line. Okay, now notice something interesting about this picture, which is if we look at Bx, right, that's group B's favorite point, that point is actually above the 45-degree line. So what that means is that if we choose an algorithm solely for the purpose of minimizing group B's error. Okay, we don't even care what we're doing to group R. In that case, we nevertheless still give group B the higher error compared to group R. So that's going to be an important property. We're going to give it a name. We're going to say that covariate vector X is R skewed if group R's error is lower than group B's error, not only at group R's favorite point, but even at group B's favorite point. Right? And this is an example of an R skewed covariate vector. We're going to say that it's B skewed if it's the flip, and we're going to say that it's group balanced if it's neither R skewed or B skewed. Okay? So group balance means that it's going to be possible, given the primitive covariate vector, to construct some algorithm that is going to give group B the lower error and some algorithm that's going to give group R the lower error. Okay. Now in practice, the way we think about group skew as emerging is if the inputs in your covariate vector are somehow just systematically more informative for one group than the other. So if you want a condition on it, you have to end up reducing errors for one group faster than the other. All right, so now with this definition in hand, we can characterize the fairness accuracy frontier. So if X is group balanced, which effectively means that Rx and Bx are on opposite sides of the 45-degree line, in that case, the fairness accuracy frontier is that part of the lower boundary of the feasible set connecting Rx and Bx. Okay. And notice that in this case, the fairness accuracy frontier actually coincides exactly with the usual Pareto frontier. Right? So if you said, I don't care about fairness, right? I just want to think about accuracy. I'm ranging over the optimal points, ranging over different trade-offs between group R and group B, you would exactly get this bolded line right here. Now in contrast, if X is group skewed, so this is an example, we've got Rx and Bx on the same side of the 45-degree line. In that case, the fairness accuracy frontier is that part of the lower boundary ranging from one of the group optimal points, it's whichever group X is skewed towards, all the way to the fairness maximizing point, Fx. So in this case, the frontier, the fairness accuracy frontier, still includes the usual Pareto frontier from Rx to Bx, but now there's also this additional segment or sequence of segments connecting that frontier to the fairness maximizing point, Fx. Okay, so from this, we can immediately already understand something about the nature of fairness accuracy conflicts. Right, so we could consider, is it possible that a point like 1/2, 1/2 would be on the frontier if it was feasible to actually achieve the point 1/3, 1/4? Right, so 1/3, 1/4 involves lower errors for both groups, but a bigger gap relative to 1/2, 1/2. Okay, can these both be on the frontier? And the answer is going to be no if X is group balanced. Right, if X is group balanced, the frontier consists entirely of negatively sloped lines. Right, this is never going to be on the frontier if this is feasible. Okay. In contrast, if X is group skewed, then so long as this point and this point are distinct from one another, we necessarily have a part of the frontier that's positively sloped. And along that positively sloped component, any 2 points are going to constitute a strong accuracy fairness conflict in the sense that one point involves lower errors for both groups, while the other point involves a smaller gap between these group errors. So if we imagine a hypothetical conversation between a policymaker and an academic, the policymaker says, look, I have a proposal. This proposal is going to decrease accuracy for all groups, but it's going to increase fairness in the sense of bringing those errors closer together. Okay. The academic can quite simply reply, are the inputs to your algorithm group balanced? And if the answer is yes, then it's really quite simple. This proposal is not going to be optimal for the policymaker by the policymaker's own preferences, regardless of how the policymaker views fairness and accuracy. Right? The policymaker could even be the pure egalitarian, and this would still not be optimal. Okay. In contrast, if the covariate vector is actually group skewed, okay, then things get more complicated. It might possibly be that the only way to improve fairness is, in fact, to make errors worse off for everyone. Okay, so how much time do I have left? Oh, 5 minutes? Okay, great. So in the remaining time, let me tell you about a special case, which is when group identity is actually an input into the algorithm. So in this case, the feasible set and the fairness accuracy frontier both simplify. The feasible set becomes a rectangle with sides parallel to the axes. And the fairness accuracy frontier becomes the line segment ranging from the point that's simultaneously error minimizing for both groups to the point that's fairness maximizing. All right, so what we can see is that the frontier is Rawlsian. Right? The worse off group is going to get its best feasible error, really no matter which optimization problem we're solving or which designer preference we're optimizing for, okay, subject again to respecting that fairness, accuracy, dominance order I set out initially. Okay? And we can say more, in fact, about the consequences for the two groups. So we can consider a comparative static, which is what happens when we add in group identity as an input. So imagine we start out with some arbitrary covariate vector x. Right? This is just one example. This might be the feasible set. This might be our fairness accuracy frontier. Now suppose I give the designer access to group identity. Okay, what happens? Well, the feasible set must expand. It also must be a rectangle from the previous result. What's less obvious but true is that it's actually the rectangle that's the smallest that encloses the previous feasible set. So now we've got this feasible set, this new fairness accuracy frontier. And what you can see is that the new fairness accuracy frontier is everywhere below the original frontier. So it doesn't matter what point the designer initially chose on the original frontier. It doesn't matter what point you're choosing off of the new frontier. We know for sure that once this designer has been given access to group identity, the error for the worse off group, which in this case is group B, right? Group B is getting the higher errors everywhere. The error for the worse off group must decrease. This corresponding statement is not true for the advantaged group. So for example, the egalitarian designer's favorite point on the original frontier is this fx. Favorite point on the new frontier is this point here. And you can see for yourself that group R's error is actually increasing when the designer gets access to group identity. Okay, so it's a short talk, so I'm skipping half the paper. I just want to give you one slide on what else is in it. So in the paper, we spent a lot of time discussing an input design problem, which is a variation on the framework where the designer doesn't actually control the algorithm himself, but instead controls the inputs to the algorithm. And there's an agent out there, like a bank manager, who's going to actually choose the algorithm given the inputs that are permitted by the regulator. All right, we're going to suppose that the agent only cares about accuracy. The regulator also cares about fairness. So the way that we model this, so this is following the information design literature in economics, we suppose that the designer chooses a garbling of the covariate vector to make legal. The agent then chooses an algorithm that takes that garbling as an input, but again chooses the algorithm to maximize accuracy. And so we ask first, how limiting is this for the designer? Are there garblings that are, okay, that second sentence does not make sense. Are there algorithms that can implement the designer's favorite unconstrained point? And actually the answer here turns out to be sort of generally yes. There are weak conditions that, that sort of guarantee that whatever favorite point you had, you can choose a garbling that's going to get the agent to actually implement that. And then we also spent a good amount of time asking whether that optimal garbling chosen by the designer might actually involve completely banning a covariate. Right? So you might say, for example, I'm just not going to send you any information about group identity so that you can't use it in your algorithm. And here we establish a couple of results. So one of these is that if X is group balanced, then actually banning group identity makes every designer worse off, strictly worse off. So in a sense, banning this input is not justifiable by any fairness accuracy preferences in our class. Okay, so then just to conclude, I've shown you a framework for evaluating the accuracy fairness trade-offs of algorithms. I've characterized a fairness accuracy frontier over a broad class of different designer preferences for how to trade off these criteria. We have some results explaining how statistical properties of the algorithm's inputs impact the shape of this frontier. And again, the main takeaway is that in some cases, for example, when inputs are group balanced, there's actually conclusions and policy recommendations that hold across this broad range of different preferences. All right. Happy to take questions. Yeah.
Time for one quick question. Yeah.
Yeah. So I think probably in most CS settings of interest, we're in the group skewed setting.
Okay.
So the optimal model for predicting Y from X for two different populations, and we see a gap in errors, right? Like that basically there's no way to like sort of cross over the line. I'm curious, sort of, whether there are some conclusions we should take, sort of, if we sort of always assume that like basically no matter how you're trading these off, like the one population is, I don't know.
Yeah, I mean, so I think it'd actually be super interesting to go to actual data sets and see whether the covariates there are group balanced or group skewed. So I don't have a great intuition for which of these is more common. I think they're both, right, because group skew, we can easily imagine that appearing, right? Because often actually the inputs are going to be systematically more informative for one group or another. Group balance, I think, the thing is that in a sense group balance is actually like a softer criterion because it just says that there's some algorithm out there that can give either group the lower error, right? So yeah, I completely agree that I think it would be cool to see which of these is relevant. And yeah, so I also agree. I think group skew in a sense is the more tricky case, right? Like so for group balance, there's these sort of like easy conclusions. For group skew, details of the designer's preferences are going to matter more. Yeah.
Okay, thank you.